Welcome to lecture number 25. And if you recall that in our previous lectures, what I was trying to tell that how to solve a differential equation, say a y, if the forcing function x t, if x t can be expressed, if x t can be expressed in exponential form, then the solution due to forcing function can be straight away written as because this is the equation. So, it is nothing but d plus a into y is equal to suppose some a into e to the power s t. Then y f t will be simply this input e to the power s t divided by this d plus a, but d is equal to s, Therefore, you save a lot of time to find out the solution due to forcing function when it can be expressed in exponential form. As a special case, if s could be complex, it does not matter, s could be imaginary or complex, it does not matter, or complex, and example of that I have shown. As a special case, if x t is equal to some constant say is equal to a, which means that a into e to the power 0 into t, s is 0, that is s is 0, then also it is valid. Okay. Then whatever, and it need not be a first order differential equation, it could be a second order differential equation, for example, d2y dt2 plus a dy dt plus by is equal to a e to the power s t. Then solution due to forcing function will be simply the input signal e to the power s t divided by this will be, now you are accustomed with this a d plus b, where d should be replaced by s. There may be exceptions, as I told you. Okay, and we applied this to find out the, because what happens is this, in electrical engineering, these sources in general will be either sinusoidally varying AC quantities, supply voltage of the grid is 50 hertz sinusoidally varying, or it could be, as the source could be a battery DC. So, therefore, when such a thing happens, then the solution due to forcing function can be written as it is. So, total solution, of course, that natural response will depend upon this one, e to the power m1 t plus a2 e to the power m2 t, and then this solution due to forcing function. Here, of course, you have to find out the characteristic roots, depending upon if the roots are distinct, it will be the nature, and we have considered several cases earlier. Now, today what I am going to tell you, recall that while explaining the nodal analysis and loop analysis, you recall these things that I told you these sources were DC, is not. Just for example, if you recall this thing. Suppose there are only two meshes are there, mesh analysis R1, R2, this is a R3, this is a E1 battery. I explained this considering the sources to be what is called constant value DC, and then the steps were like this. There are two meshes, you assign the mesh currents which are supposed to be the unknowns. Then the writing down KVL equation in mesh 1 will be simply the coefficient of I1 is R1 plus R2 into I1. Then coefficient of I2 will be the common resistance minus R2 into I2. And that will be equal to the sources on the right hand side, and the sources where the direction of I1 is this way. So, it will be plus I1, and direction of E2 polarity is such that it opposes I1. So, minus E2. Similarly, the KVL equation in mesh 2 will be the coefficient of I2 will be sum of all the resistances, that is R2 plus R3 into I2, and this is plus, and coefficient of this one will be common resistance into negative sign, and this will be equal to E2 minus E3. Then you solve these two equations and get the currents in various branches. So, we have discussed that. But now, in the present scenario, for example, now we consider, okay, if there are time varying sources present, if there are inductances present, capacitances present, whether this kind of rules will be, still we can do something with these rules. The idea is that, recall that in an inductor, if you recall an inductor, if this is the current and this is the value of L, then voltage across the inductance with this side plus this side minus is L di dt. Okay? Suppose this point is A, this point is B. And since these are energy storing elements, some people say that okay, this can be treated as some source voltage also, no problem. You show it as a source, because after all energy storing elements, which are the sources which can supply energy to a system. Therefore, the conventional sources are batteries or grid supply voltage, that is there. But because inductance can store energy, capacitance can store energy, and we have seen that even without these conventional sources like battery and grid is not present, but inductor with some initial current, that is with initial energy stored, will still be able to drive current in circuits. Therefore, they can be also treated as some source, and so we can treat this as it is a voltage drop, no doubt L di dt, but I can show it like that, no problem. So, remembering this, now let us see how can I write down the KVL equation when inductances are also present. For example, first let us take a simple case. Here is an inductance L1, here is an R1, here is R2, there may be what not, any other sources plus E, and there is another source here, another inductance there L2, and another battery, like this. And here is a source which is time varying, plus minus V t is the applied voltage, supply voltage, which could be any time varying function. So, this circuit I have to solve, and suppose I say that I have learned this mesh analysis, why not apply it here? Now, first thing is, in this case what you have to do is this, you assign the mesh currents, and it is expected, since the source voltage is time varying, currents in these circuits also will be time varying, and it is customary to represent time varying current with small letters. Generally people do not write capital I1, capital I2, small I1t and small I2. It is expected they will be function of time, because energy storing elements are present. Now, the question is, I want to write down the KVL equation in this one. So, this is then this you have assumed I1. So, voltage drop across the inductance will be L1 dI1 dt, and voltage drop in this inductor, see I2 is flowing. So, plus minus L2 dI2 dt. Once you do this, and suppose this voltage is E1 and this voltage is E2, then I will once again apply the same technique in this way. See, coefficient of I1, so far as resistances are concerned, it is fine. I will write it like this, that is coefficient in mesh 1 in mesh 1 KVL equation in mesh 1. It will be sum of the resistances R1 plus R2 into this small I1, that will be there, sum of all the resistances. Do not add R1 plus R2 plus L1, then you will be making mistake, because the voltage drop across the inductance is L1 dI1 dt, not I1. So, okay, with resistance this is what we have learned. So, this will be the coefficient of I1. What will be coefficient of, this is suppose R3, coefficient of I2, it will be minus R2 into I2, is not? This will be the coefficient of I2. And then this should be equal to all sources I will write on the right hand side. So, as you can see, it will be the polarity of supply voltage is such, I will write VST the same way as I1, capital E1 minus E1, we know this. And then there is another source here, because it is L1 di dt, treat the inductor voltage drop to be source, and then the polarity of this source is such that write minus L1 dI1 dt. So, by inspection I am writing now, that you must understand. So, this will be the mesh equation here, and in the second, in mesh 2, KVL will be equal to coefficient of I2 will be equal to R2 sum of all the resistances plus R3 into I2, that is there. Then this is plus, and coefficient of I1 is minus R2 into I1. So, minus R2 into I1 and sum of R2 plus R3 into I2, and on the right hand side all the sources will be written, including the inductance voltage drop. So, it will be equal to, as you can see, it is E1 plus I2 minus E2 minus E2, and the polarity of this voltage is minus L2 dI2 dt. So, this will be the KVL equation. One can use the same concept as that one, only thing, since things are time varying, it is not all terms are I1, there is dI1 dt. So, there will be differential equation you have to solve. And how to solve differential equations? We know that. So, you have to eliminate I 2 from one equation, get the eliminate I 2, write it here and form a differential equation with I 1 alone and then solve for I 1, then I 2. So, this is the idea I am telling what you can do. Similarly, nodal analysis. Nodal analysis also in the same way you can write. For example, I will say that I have a circuit like this. So, circuit may have DC voltage, AC voltage all connected together. There may be time varying voltage also. This is R 3, this is R 2, this is R 1 and here is your supply voltage plus minus VST time varying. And I want to apply nodal method. Now, in nodal method, how many nodes are there? I have to first identify. These are the two nodes where more than 3 ends of 3 elements have been joined. This is also a node, but okay, this is a node, this is a node, because current in this branch is same. And one of them you choose as the reference node and this as the other node. Okay. Now, here once again and this is suppose L. So, what we have been doing so far that okay, this will be the thing. Now, I have to write down the KCL at node A. Is not that is VAO is the unknown VAO, this node voltage. So, what will be the coefficient of VAO? We used to say that it will be sum of reciprocal of all the resistances connected to node A, is not? There is only one node, so there is no problem. So, that way we used to tell that. Now, but here is now an inductor present, not only R2, there is an inductance. Suppose I say that this current is IT, because I am not sure whether I will write like 1 by R1 plus 1 by R2 etc. So, KCL at node A, let VAO be the voltage, then this current flowing from right to left in this branch will be VAO minus VST. Let us write from fundamental, this divided by of course R1, this will be the current. Now, this current will be plus, I cannot write VAO by R2 because there is this fellow present, and if it is carrying some current, here is some voltage. How much is the voltage? L di dt. What is I? I is the current flowing through the inductor, then this will be the current. So, this plus this current IT and plus here no problem, because VAO minus E2 by R3 and this must vanish at all times. So, this is the equation. Now, therefore, you see, or the coefficient of this one VAO will be 1 by R1 plus 1 by R3, that is this term and this term, into VAO. Then plus IT is there, and on the right hand side we write the sources VST by R1, no problem, VST by R1 pushing current there, and E2 by R3 plus E2 by R3, isn't it? This will be the thing. So, it looks like there are now two unknowns apart from this VAO. There is I must know I. Now, if you see, you know that VAO, I told you several times, to find out potential of point A with respect to O, you start your journey from O and reach the point A via any path you like. Now, I will choose suppose this path, then VAO will be equal to from this to this, it is L di dt plus R2 into this I, is not? This is the VAO part. Got the point? Potential of this point, this node with respect to this is start your journey from this to this, you get L di dt minus 2 plus, then from this to this once again minus 2 plus, that is R2 into I. This will be the drop here. So, this is the other equation. Therefore, I can substitute for VAO this quantity and get an expression for the current IT alone, and it will be as usual a second order differential equation, not second order, a first order differential equation, and then I will solve it by the method we have learned. So, essential thing is you have to form a differential equation correctly. For example, what here once again this circuit can be drawn R1, this is R2, no doubt this is R2, and this can be written as a source plus minus, but this source voltage is L di dt, mind you, is not? That is what I told you, because after all inductance energy storing element, so L di dt, and this you can write it as a source plus minus L di dt. That is what I have done here, L di dt. This was R3, this was your E2. So this is your supply voltage, which is like this. Therefore, if you treat it as a source, but what is this I? I is this current. I is this current. Therefore, the rules that we have learned earlier can be straight away applied. Why? Because I will say that this way I will say that coefficient of A VAO will be sum of all the resistances 1 by R1 plus 1 by R2 plus 1 by R3. This will be the coefficient of VAO. No, this is there, and coefficient and that is all. This is the thing, only one node, this will be the thing, and this will be equal to the sources connected. So, VST divided by R1, current drives there, plus this voltage, here is a voltage source here also, L di dt, this voltage divided by R2 will be the current going there, is not? and plus another source is there, which also pump current, the polarity is such it is trying to pump current to A. So, that is why plus E 2 by R 3. You know, this is one and the same thing. See, the same equation so sometimes what you do, you replace the inductance by showing it as a voltage source, L d I dt. But this equation has two unknowns, VAO and I. Then the other equation is this one, this one. Anyway, you will gradually be habituated with what I am telling. So, nodal, once the current is known, similarly with the capacitors. If capacitors are present, you can find replace that capacitor. For example, loop equations, I will just tell like this. Suppose you have a capacitor, I will just give one example. And here is a voltage source, which is suppose time varying VST. Therefore, I want to solve this circuit R1, R2, R3, and here is a capacitor. Okay, I want to solve this circuit by what is called the mesh analysis. Mesh analysis. So, for capacitor, you generally choose the unknown as the capacitor voltage, is not? That is what you choose. But once you choose that, this current from top to bottom, this current I will be equal to C dV dt. I am ready with this equation before I start solving. Okay. You have assumed this to be voltage, then the current flowing into the positive plate of the capacitor is C dV dt. That is there. Now, there are two meshes. So, you choose this mesh current to be I 1, this mesh current to be I 2, small letters because things may be time varying. So, I 1 t, I 2 t I choose as a function of time. Then I will apply the rules, mesh analysis. So, KVL in mesh 1 will be equal to sum of all the resistances, that is R1 plus R3, that will be the coefficient of I1, coefficient of I2 will be minus R3 into I2, that will be there, and on the right hand side all the source voltages. What are the source voltages? VST plus, because I1 is flowing like this, VST, and there is another source voltage VT minus VT. Similarly, for the second mesh, it will be equal to coefficient of I2 will be R2 plus R3 into I2. I am so sorry, these are all small letters. So, this is I1, this is I2, and this is R2 plus R3 into I2, this is the mesh current I have assumed plus, and then this is minus R3 into I1. That is fine, and this on the right hand side the sources will be VT minus E, is it? That will be the thing, and these two equations you have to solve. But there is a third equation needed. Here this source voltage, this VT depends on I. So, so I is nothing but, this I is nothing but I1 minus I2. So, this I is nothing but I 1 minus I 2. So, you have got, you can translate this into this one wherever I will be there, and you can have essentially 3 equations 1, 2 and this 3 equation with small I is equal to I 1 difference I. Therefore, that is what I want to say. This equation is I 1 minus I 2 is equal to C dV dt. This is the third equation. How many unknowns are there? I 1, I 2 and V. How many equations are there? 3 equations. So, I will be able to solve for either I 1 or I 2 or V. So, I 1, I 2 and small v can be solved, Therefore, the restriction we put for applying nodal and mesh analysis can be removed. Okay, after all, what is there? Because the interesting point is KVL and KCL will be valid for all time to come in a circuit. That is, the sum of the currents at every instant must vanish at a junction, and similarly sum of all the voltages in any closed loop will also vanish to 0. Anyway, there will be several problems will be given, and I will conduct a tutorial class also based on this. So, hope you have understood this part of this circuit analysis, and we will proceed further in the next class. Thank you.